So we are going to keep doing maximum minimum stuff. I think this is the last one here, and then we move on to Lagrange multipliers. We need to have this before we can do the lab. So that's why I'm not doing the lab today because we need to do that first. Anyway, I gotta say this one's leading right into the next section. So I'm gonna say Lagrange multipliers uses this exact style, and so it's almost as if I want to teach this and then go back and do this one, but we're not. Find the maximum value of this. Win that. I think what we're gonna need to do is like take some derivatives, I guess. So as maximum value of s, wouldn't that be hold on? Wouldn't that be s prime equals 0 essentially? Solve for x, solve for y, solve for z. That's what we're kind of wanting to do. So how do we find s prime? Implicit, that's the best we got, right? So let's try that. Let's see what happens. So s prime or ds if you're wanting to be all technical, right? It's better to do that. ds. Help me out. Here we go. Okay, yeah, let's do, I'm going to do like this. How about this? Let's do derivative in terms of x, right? So we got a y, and then we also have the z, right? I'm doing this differently. I'm doing it like pre-factored, I guess you could say. I'm just saying, let's run through the x's. Let's run through the y's. Let's run through the z's. So then if I did y's, I would have a and then my z's I would have perfect. So that way it's all kind of grouped together, I guess. Looking at this thing, I'm thinking that I can like do some derivatives with that maybe. And this is kind of weird. Like, if I wanted to take the derivative implicitly, then what would I be getting? One dx, yeah, one dy, one dz equals 0. Very good. That's kind of weird. Is that going to help me? I don't know. I feel like there's way too many variables going on, right? Way too many variables. And so maybe there is too many variables. Maybe there's a way that we can back off of this and do something a little bit better. So here's an idea. I don't want to like totally erase it, but I want to say, let's try something new. Because what I'm running into is like, I don't know where to go now. Does it make sense? Turn around, don't drown. What if I did this? Yes. And then I did this. What do you think? If I solve for z, plug it back in. Now I've reduced it down to only x's and y's. Maybe that's better. And maybe we can figure something. So I'm going to rewrite it, xy, and then I'm going to do this stuff here. Okay. I know you don't like this, but I'm going to do it anyways. Simplify. I know, right? Gosh, man. You would think you'd be accustomed to it at this point. But no. You've gotten all this, like, Cal 3 gloating. That's what it is. Yeah. Oh, well, I'm in Cal 3 now. I don't have to simplify. But, like, look around. I think some of this actually kind of gets nicer. Notice that we had an xy and we have a minus xy. So at least that's something. I don't see too many other things. Oh, go. Yeah, I know. I thought they would cancel too. So let me group them, I guess. Let me group them to like my x's and my y's. And now I could take a derivative with this guy. Actually, you know what? I don't want to do implicit right now. Hold on. We have two variables. We have an xy, right, at this point. Don't we have a formula for just x and y? Like, that's kind of like what we've been doing for all the other stuff. Right here. At least that much. See how we have just x and y, right? And it says do your derivative with x, set it equals 0, and do the derivative with y, set it equals 0, right? What if I just did that? And maybe I could do this stuff later. I mean, it says find the maximums, right? So it's probably going to end up being that is the only answer. I don't know. We'll see. But what if I just do what we were supposed to do instead of being so funny? Ah, thank you. I would have gotten it wrong. Thank you. Can I add more points back to your? No, I'm playing. No. so, so I'm gonna do Sx. I know it's like f sub x. Negative 2x plus the 12. I'm gonna set that equals 0, and then I got my s sub y is. Oh no. Messed it up again. There it is. See, I keep doing the same mistakes. And I need both of these to be working. I need this and that to be equal to 0. And that's okay. So we have a system of equations now. That sounds fun. What would you do? Since we have a pretty simple on the sure. I like that. Yeah, I like that. Let's do that. I'm going to switch colors now. So then from here, I would have y equal to this business here. And then I could plug that in to the other one. So I'm going to plug that into the second guy. So I basically, I took this and I plugged it in right there. Distribute. Y'all make sure I'm not going to do something dumb. Because I'm prone to doing that. So we got a 4. That sounds cool. I mean, it was a nice, easy number. So far, so good with that? If that's the case, what would my y be? Yes, or we could just say the y equals formula we already got from Sx, right? Yeah. Yep, as expected, and I'll tell you why I expected it to be the same. If you go and look at kind of like the holistic view here, is there truly a difference between x and y? Not really. There's no coefficient difference. Whenever there's an x, there's like a y that kind of does the same thing. So if I got x to be a 4, I better darn well get a y to be 4, And I only got a single number, so that's kind of nice. Basically, I'm ending up with a single answer here, 4, 4, and, well, whatever z would be. Actually, we can find that. What would... Oh, I was going to say just plug it in. What we get is a 4. Because is there any difference with the z's? Not really. They're all kind of doing their own same thing. I'd almost want to call it symmetric in a way, right? They're all symmetric unto themselves. So this is where that maximum exists. Now I actually have to plug it in. So S of 4, 4, 4 would be 16 plus 16 plus 16. Because it's 4 times 4, 4 times 4, 4 times 4. Is that 40? 48, thank you. I was about to say 42. 48. Let me go real quick, flash the answer. I forgot to pull this up real quick. 48, there it is. We got it. Cool. So, in a way, I love doing this implicit stuff, but in the end, I don't think it's as helpful. I think better is to follow like a formula of some kind. and that's okay. Hi. Yeah, you can come on in. What's up? The key to what?
Do you know this non-sticky, the one?
Oh, I don't have that. No, I don't.
Yeah,
Sorry.
just looking for it.
Oh no.
Yeah.
Okay. Thank you. That's not good. But y'all don't have to know that. Are y'all okay with this? What I'm learning is that I should probably stop being silly. I should just go right to a formula, right? That's what I should probably stick to. Cool? I love doing the concepts, but in the end, it's just, yeah, formula's better. Okay. Any questions before I move on to more formulas? Yeah. Go ahead. Well, in a way, let's do a zoom out for this particular problem. Notice that they're all about the same. Even here, they're all about the same. So I'm saying I got three numbers all add up to a 12. 4 plus 4 plus 4, right? There you go. And what we'd had, at least in the WebAssign class on this section and the next one, is a lot of application questions where they were boxes. And so find the volume, maximum volume, find the maximum surface area, that kind of thing. A lot of those good stuff. I don't think we're going to see that here. Sorry, but you can see that, like, what's the maximum volume is like a cube, I guess you could say, right? Or a sphere, and you can take these shapes and just get an answer. You don't have to think about it too much. Okay, Lagrange multipliers, or Lagrange, I guess, if you're wanting to be cool. This is the biggest formula ever, right here, but it's tied in with this little dude. Okay, you actually have to have both for this to work, and I know that they don't. It's more like this. That's actually what I would say is the formula. So that's a lambda. That little dude right there is a lambda. It's just an L, and it's just a scalar. Now, lambda doesn't mean scalar, but our particular lambda here is a scalar. Why is it a lambda? Because they ran out of letters. So there you go. They just I know, because it's Lagrange. So it's a lambda because of Lagrange. There you go. I literally just thought of that. So yeah. Nope, nothing to do with Half-Life. Yeah, we just reuse the Greek letters because we don't got enough of them. So yeah, L for Lagrange. That's the first time I've realized that in, 24 years. So, and E is for Euler, right? Y'all don't know that? The little E, it's for Euler, because he's the one. Yeah, it sounds like Euler. No, my previous professor would have gotten the ruler out. Whapping, yeah. That is a no-no. It is Euler. It's German. Yep. I don't even know if he was German, but he was very particular because that was his favorite mathematician, so he was all on it. Anyways, so here's our formula, and it's kind of confusing and it's weird. We're gonna there you go. I don't know about this guy. I don't know if I'll ever use this one. Depends if they have two G's or not, but in the end, there's an extra one just in case. Okay, let's try it. And I gotta say, looking at this problem, we can do it the long way. In fact, I want to do it the long way first. I want to do it with the stuff that we just learned last section. It's even set up for us, guys. Look, it says F and it has the X's and Y's. I'm telling you, we're going to do this not Lagrange. I'm going to say right here, not Lagrange. And then we're going to do the Lagrange in a few minutes, okay? So not Lagrange is that we have f sub x equal to 0, f sub y equal to 0, right? And you need both of them, and both. So let's do that. What's my fx? Okay, awesome. Fy? Awesome. Okay, and I need to set these equal to 0. Cool. So what is my x and y equal to? Yeah. So in a weird twist and fate here, this is the only answer I came up with, right? And so it says, what's the maximum value? And I want to just say it's 40 because I plug it in and it's 40. Let's go see if that's the case. Okay, let's go see. I'm a little nervous because it was way too easy. Oh, okay, that's fine. That's fine. So, the reason why so far it's not working the way I want it to is because they have this line constraint and I never used it. So maybe I forgot something there. Okay, maybe I went too fast. Let's try something new. So I'm going to erase all this because it was wrong. That's okay. Let me try something new. What if I do a tiny bit of system of equation things? Okay, in a way, can't I solve for one of these variables here? And that I would recommend that because x is easier. Let's try this. I could take this and I could plug it in right there, can't I? So in a way now I can rewrite my f as 40 times this, 40 minus this stuff here, and then minus this thing here. What I'm wanting is the maximum value, so I'm wanting f prime equal to 0. This is literally calculus 1 now, right? I'm not even doing a cal 2 formula at this point. This is just cal 1. So let's try to find our derivative. The 40 goes to 0. What do I get out of this junk? Yes, yes. Power 1 now, and then times. Perfect, perfect. And this guy. Perfect, perfect. Set this whole thing equal to 0, and let's do this guy. I actually want to do like a calculator because I'm just like, I want to see the answer. But let's, like, looking just like broadly at it, do you think 0 is going to be a good answer for this? Probably not. And so maybe we are going down the right way finally. So let's see. I got 2 negatives make a positive. So I got 12 times this stuff here, and then minus the 2y. It's still just linear. But I do need a calculator for some of this stuff. Hold on, I need to get this ready. Yeah, don't write anything until I see if I'm right or wrong. Especially if you're using pen in a math class. Yeah.
Oh, I plan on doing the. I'm writing it in red, so I know that it's wrong.
That's why I'm in red too. Yes, and it very well could be still, and I'm okay with that. I'm wanting to try to avoid Lagrange for a good purpose, and I'll show you why. I do this whenever I do teach this. I do teach this like this, like this whole little game of let's try to not use Lagrange for a couple minutes. So if I did 444 divided by 74, right? And if I had this guy here tied in together, my x would be, see how I'm getting different numbers now? They're not just 0, 0. And if I plug those in right here, so I'm going to say f of 1 comma 6, 40, 1 squared, 6 squared. Was that their answer? 3. Look at that. We got it. We did it with calculus 1. We did it with calculus 1. Okay. Now, I'm not saying that what we just learned in the last section was wrong. I'm saying that it went too far. Yeah. Start with cal 1. If that doesn't work, go to cal 3. And if that doesn't work, then we go to Lagrange. So why am I avoiding Lagrange here? Is because it's scary. It's scary, literally. And I'm going to show you. I'm going to go through it. I get nervous with it. I don't get it right very often. But if you use techniques from Calculus 1 in earlier sections, you can almost always avoid Lagrange. Okay, but it's designed to be easy, at least on some level. So we're going to try it right now. Good. It's no longer wrong now, huh? Should I change it all into a blue instead of a red? Oh, okay, thanks. I guess. As long as it shows up, you know. So, yeah. Oh, good. Copy it down now. Now that we know that it actually worked, Mason's getting at him after it now. So yeah, I'm gonna wait. I'm gonna wait for just a minute before we do this. Good. Is this making sense though? Right? Solve, plug it in, do a little derivative action. And it's okay to try different attempts. Turn around, don't drown kind of stuff, right? If it doesn't look right, do something else. That's okay. That's what we're supposed to do here. Are you actually like doing Lagrange right now, or am I just waiting? Oh, you're just copying. I'll wait until you're done because we're gonna start doing some craziness here. We're fine. I don't mind waiting. I'm okay. Oh my.
Which I don't know the math behind, but I know it's notoriously very convoluted. So
This is going to be convoluted too. Yeah. This one will be an easy one compared to the other ones. Yeah.
Lagrange probably convoluted.
Yeah. Oh yeah, yeah. And either way, I'd say, are you good now? Excellent. So I almost need a lot more room. So if you don't mind, I'm going to erase. Is that okay? I'm going to get rid of all that, and we're going to basically. Oh, okay. I thought you sighed. Anyways, yeah. Let me just get rid of it all, and we're going to do the real stuff. It's good to practice on an easy problem because when you get to the harder ones, it'll be a little lumpy. So let's do an easy problem like this. Let me rewrite my formula. I got my grad f is equal to lambda grad g given that g is equal to 0. So first off, I need to define what f and g are. And they're kind of nice about it, right? We got f. That's easy enough. But what's my g equal to in reality? It is equal to 0, but it's also variables. What would it be here? Very good, very good. Now the minus 37 will go away eventually, but if I had to give a g, that was what it would be. I need to make sure it's equal to 0. Okay. Again, this is an easier problem. I'm not worried too much about it, but you have to make sure it's equal to 0. Okay. Cool. Now here we go. Let's just do the formula, I guess you can say. So grad f is my derivative in terms of x and y in the x and y slots. So this is like fx and this is fy, right? So what's my derivative in terms of x? And then, oops, you said it, and I didn't do it. And then for y, yes. Let me go ahead and I'll put it right down here. Sometimes I want to put it beside it, but that's fine. Grad g. So when I'm looking here, what's my derivative in terms of x? And for y, 6. Very good. So it's like I kind of want to like set these equal to one another, almost. And you can kind of see how things are going in a way. So then I'm saying that we have negative 2x, negative 2y is equal to lambda times this stuff here. You already know what the answers for x and y are, so you can kind of see something trending here, I guess you can say. Take a stab at it for a second. Think about it. What do you think lambda, as a number, it's just a number, right? I don't know what that number is yet. If you had to pick a number for lambda, just take a guess what it would be. You already know what the answers were. 1's a good start, right? Because we already have these numbers, so don't mess with them, right? But because these are not simply x and y, we have to do a little bit of manipulation. You're right, though. What? Negative 2. Because, and again, this is only because I already know what's happening. Okay? Not all the time I do this. But couldn't I say, oh, they both have a negative 2? And you can see now that lambda is equal to negative 2. In a way, I'm kind of like canceling it in a way where I can say x is 1, y is 6. Leave them alone, right? Don't touch them because those are my answers. Plug them back in and get the answer. That's the zoomed out version. You cannot do that every time. You can't. but I just want to show you lambda is a number. We're trying to solve for a number here. Do you understand my stress on it? It's just a number. It's like solve for x. I'm just solving for lambda. And this was an easy one. Let's make it harder instead. Let's just assume that I did not know how to do that, okay? So I'm literally erasing that because that was great, but only this one time. I now need to break it down into individual components. And what I have to do, of course, is distribute my lambda. So I got negative 2x is equal to lambda times 1. And I got negative 2y is equal to lambda times 6. And now I'm making a system of equations. The easiest way to go forward is to solve for lambda. So like right here, lambda is equal to negative 2x. And I take that and I plug it back in. And that's the easiest way, right? What that does is it gets rid of my lambda. Look, oh gosh, go away. Like seriously. Thank you. Okay, look at this right here. Do you have any more weird lambdas in there anymore? Isn't that just a normal solve for x kind of situation? Pretty much. At least I hope so. What can I say about all this? Can I simplify this down a little bit? There you go. That's what's really going on. I could divide by negative 2 on both sides. Reverse. Right. I mean, it's close to that, isn't it? Y is equal to 6x. That's a relationship. Again, I am going way too much math here for an easy problem, but in the future, we're going to need this. So I have a relationship here. We also have this. And so now it's come back here. Here's like my final answer section. I'm saying that I have this guy and I have this guy. And now I'm literally just solving. Plug it in, get an answer. Here we go. So I got 6 times 6x here. That's 36. 37x is equal to 37. X equals 1. I could take that and plug it back in. So y is equal to 6 times 1 is a 6. I take both of those and plug it in. 40 minus 1 squared minus 6 squared is the 3, and we're done. So the goal here is to set up my equation, solve for lambda, and then like plug it back in. It's just like, it's kind of like two systems of equations in a way. Right. Oh, yes. Yes. Because you'll have 3 lambdas. And yeah, things get a little bit iffy. So, yes, yes. No, always the same number. It's a single number, a single scalar. Yep. Yes. So here's how I view Lagrange. You have x and y as your variables. Lagrange is adding one more variable. It says you had x and y, good. Let's add x, y, and lambda now. Have fun. It's adding complexity to the problem that you did not need. But with that extra complexity, I can kind of, work it backwards enough to get the answer. And so what if I gave you x, y, and z? Now I'm adding a 4th variable in there. Have fun, right? Well, now it's just more work, but sometimes that's the only way to get it done. Yeah, look at this crazy math when we could have done Cal 1, right? Which we did. It's okay. Any questions? Good? Okay, go ahead. Well, turn around, don't drown, essentially. You keep trying other methods and it's not working. This would be the last method. I would say don't do this all the time. Yeah, good. That was a good question. Yeah, it's definitely a last ditch effort. This is the last section. So, okay. Find the dimensions of a right circular cylinder with maximum volume and a sphere, blah, 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 inscribed. What? I think we need to draw a picture. So we have a right circular cylinder. It's a cylinder. Okay, so that's what we're looking at. That can be inscribed in a sphere of radius 16. That's what I'm thinking. That's what I'm thinking. So I mean, my sphere is now an ellipsoid. Hold on. Let me start over on that. Sphere, right? Still kind of egg-like. Looks like an egg. I want. Yeah, yeah. Just in case you're wondering, that's supposed to be a sphere. Ew. I think I really made a really good egg though, so that's awesome. Um, so 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 from the very center, my radius is equal to 16. Um, and I need to find the maximum volume of this thing. Okay, and then once I do that, how big would it be? Okay, okay. So I think what we need is some formulas, right? First off, we need a volume formula for the cylinder. What would that be? 2 pi 2 pi r h is the outside rim, or yeah, the yeah, circle part. Let's just use r and h. I think that's fine. We can use a different number for that later. That's good. Plus, so that's this thing. Oh, that is it. No, hold on then. I don't like that. That's surface area. Pi r squared h, because we're taking an area and we're multiplying it by height. Okay, yeah, you were doing surface area. That's okay, but I didn't know it either. Yeah, so that's my volume of a cylinder, and I want to maximize this. This is a very important thing to write that down because we're going to do something else here in a second. I need a second equation. So I have my volume, that's what I want to maximize. But I need a second equation, some kind of constraint. What can I say now? Okay, that is definitely one way to approach it. How would I relate that back to the cylinder in a way? Because see, I'm using these as my cylinder stuffs. Here, how about this? I think my picture's not super great. Let me try something else so that I can maybe like show you what I'm thinking here. So what if I had it more like almost like a tuna can? Okay, I know that tuna cans are even shorter. Let's say more like a tuna can for a second, and then, man, me and my eggs. Um, let me. Okay, this is it's closer. It's closer. If you just draw enough circles, right? Um,
You know, Chad, I got a question. Have you eaten breakfast today? Something's telling me you're kind of hungry right now.
my bigger point is that the cylinder should be touching the outside, not just there, but even like right here on the back side, right? Isn't it basically this and this are being touched the entire time by that sphere? Um, so yes, it's kind of like I made a sphere, like a normal ball, but then go ahead.
One thing I'm thinking is kind of finding a value between having the height equal 16 and the radius of the volume of the can be 16.
Right, you're getting there. That's exactly right.
I'm trying to find the in between point that maximizes the volume.
Yes, that's exactly right. The equation that I'm looking for is going to make this corner or this tip, these edges, to be 16, right? From the center outward, it should be 16. So if I made it in 2D, I'm going to say this is in 2D. I'm saying from the center out to a corner, this should be 16. Are you in agreement with that? Because that's where the sphere is going to be touching. it's going to be touching there, and that's this radius of 16. So opposing corners. So then in 2D, how would I actually make that equation? Let me draw the 2D one more time. So again, from the very center of the tin can out to here, that's 16. How can I say that in an equation? Probably. Here's an idea. If this is supposed to be the cylinder, right? This is the cylinder. Then from here out to here is how much? Radius? Just radius, right? R. And how much is this distance here? Very good. It's half my height, right? So then maybe I have a triangle going on, don't I? Literally, right. Triangle. Right. So then let's do that. Give me the equation. What would it be? Let's not go square roots. Let's just do the easy one. Very good. All squared. Very good. All squared. Yep. Very good. Yes. That's my other formula in a way. Let me write it down right here. So I don't want to put an equals. That's not right here. No. I'm going to have r squared plus h over 2 all squared is whoa minus 16 squared is equal to 0. This is my constraint. This is my f. This is my g. Now we're ready for Lagrange. I'll do it for the Texas side and for the French side. How about that? Are y'all kind of seeing like a zoomed out version of us going forward with Lagrange at this point? We have one that will be maximized. The other one is simply a constraint. It defines how we're going to do stuff. Now it looks messy, especially that constraint, but that's what we're going to do. Can I do it without Lagrange? Okay, here, let's take a vote. Do you want me to do it Cal 1 style, or do you want me to do Lagrange style? Cal 1. Lagrange? All right. You mean you got to be a good teacher? Gosh. Almost always you can avoid Lagrange, but I don't want to have to do that. Sometimes it gets messier going around him. So, yeah, let's be a good students and do the actual proper math. And it will end up better in the end, I'm sure. Let me simplify this a little bit more, if that's okay. What would I have? What would be my coefficient in the front? This is h squared, but what would I have right here? Yes. And then 16 squared is 256, I believe. So that's a little bit better for me to do derivatives and stuff, because we will be doing derivatives. Let's do this thing. So I'm going to say grad f lambda grad g, and we already have g is equal to 0, so we're good to go. So grad f, what would I be doing? Let's do r and h, by the way. So this will be, you know what? I want a new color. Hold on. The orange, it's fine, but I want blue right now, because I feel like we're like moving on to the next phase. So again, this is going to be FR, and then I'm going to do FH. You know, it's kind of like X and Y, and you can use X and Y if you like it, because I mean, isn't this kind of like an X value? Isn't this kind of like a Y value? I would totally be fine with that. I'm just trying to keep with what we got. So what would be my derivative of this guy in terms of the R? Which we had earlier. You just already had the math ahead of time, right? That's what it was. I'm sure there's a paper on that.
Does that apply only to the cylinder?
When I take a derivative in terms of h,
You would get pi r squared.
sweet. Okay. Grad g, in terms of r, what do we get?
That would be
Yes, 2r. Excellent. And then my h?
that'd be 1/2 h.
1/2 h. Good. Doing the math already. Okay, awesome. So then let's mush them together. So I'm saying that, man, yeah, let me just use this little bit of room, and I'm going to go back over there. So grad f is equal to lambda grad g. I'm saying the 2 pi r h pi r squared is equal to lambda times that stuff. I'm just kind of rewriting it so I feel better about myself. I'm not actually doing any math there. But there's two individual equations now. I got 2 pi rh is equal to lambda times 2r. And then I have pi r squared is equal to lambda times 1/2 h. Many different ways we can go here, but I recommend an easy way. What would you want to do to go forward solving that stuff? What would make you most happy?
Wouldn't it be easier to simplify if we move the 2r to the other side, then we can find lambda?
Yes. If I move it to the other side, what do I get?
You would just get pi.
Yeah, pi h, very good. That's exactly right. I'm dividing this to the other side, and like in a way here, I'm gonna use a different color to accent. You're like canceling those guys out, and there you go. Divide on both sides. Makes it really easy. Then I can take that and plug it back in right over there. So now I got pi r squared is equal to pi h times 1/2 h. A little bit of simplifying. There we go. My r's are not very pretty. And your pies aren't either, Chad. Okay. By the way, for online folks, that was me making my own joke. It's okay. No one was telling me my pies were bad. No pies were hurt in the making of this film. Actually, they will get hurt. What happens to my pies? They're gone. Exactly. Whoosh. I know y'all did something similar to this in Cal too. Thinking wine bottles. Got the shivers about that lab.
PTSD flashback right there.
What how do I get this easier looking? What should I do at this point? I know, I'm going to rewrite it so you can see more clearly. I want to make it easier. What can I do with this thing? Square root both sides, and notice that I'm going to get a plus and minus, right? But like, we don't need that. We know that our answer is going to be positive, right? So if I really wanted it, if I square root, I don't get that, do I? Oh, you know what? I'm going to simplify on you. Oh, you're going to hate this. You get square root 2 over 2h, plus or minus technically. Oh, that takes the fun out of it. That makes it easier though, doesn't it? You're right. But I gotta say that even this step right here is probably unnecessary because I need to be looking forward a little bit more. Watch what's going to happen now because we're not quite done. What we need to do now is use our constraint. And look what it has. Aha. So I didn't really want that, actually. I want this. I know, right? I'm just making a big deal about it, but it's like not a big deal at all. Let's plug them both in together. So my r squared is 1/2 h squared. And that's literally all of this r squared this is it. This was all r squared. So I do not re-square it. I leave it alone now. So I've got a half plus a fourth makes a what?
Wouldn't that make 3/4?
Yeah.
Oh, you already had that.
I know. I'm just being that way today. 256 times 4 is 1,024, I believe. And then divided by 3. Hold on. I might actually be able to get this one. Is it 368? Let's see it. Nah, you don't need that stuff. Oh, actually you do. So, dang. Okay, that's fine, I guess. All right. Well, that's just they say just stop there. Okay. So h squared is equal to this big number divided by 3. And of course, we square root, as you already know. So then the square root of that should be 32, I'm guessing. Yep. 32 over the square root of 3. Yes.
You could just drop the 3 in the denominator to get the answer. Oh, I see. You simplifying the numerator. Okay.
Yes, I did simplify the numerator and just the numerator. This actually did come in handy because now I can just plug in my h, right? So my r should be square root 2 over 2 times 32 over the square root of 3. And I know that things will, make it look nicer later, but there we go. Let's go and check the answers because it's a little bit on the weird side right there. So here we go. Flash the answers. We got, ooh. So this one here, yes, I confirm with that, right? Because you just pop it in the top, leave the number behind. So that one's easy. So if here I move the 3 up, I get square root 6 divided by 6. Square root 6. Oh, and they canceled the 32 and a 6 there. So yeah, confirmed it works. There it is. I almost want to do this because I know you're taking pictures. Can I do that so we get the picture there too? A little bit easier. So bigger picture here is this was a tougher problem simply because it was an application problem. We had to go and find these other equations, which makes it fun. And it takes 20 minutes to do. I'm impressed because I was worried that this would be far too easy, but this one actually is holding up a little bit. I like to see more of this. Any questions? Can you do this without Lagrange? Probably, but I don't want to now that I got the answer. But I mean, if I had done it the easy way first, then I probably would have went back. But here I went the hard way first. So. Are y'all okay? No, I don't want to say comfortable, but are y'all okay with discovering this extra constraint? It's a little out there, isn't it? And that takes a little bit of practice for sure.
To be able to understand what you're asking.
Exactly right. Yep.
Because initially reading it, I was kind of thinking the sphere was inside the which would have been
You're right. That's my first thoughts too. There are other classic problems where you have cones and you have a sphere inside of the cone. So that's another classic one that we have to look out for. Yes. Okay. Let's see what else is ahead. We only got 5 minutes, but temperature point. Oh, okay. Well, this is way easy because they just give you the formula. Look, I'm half playing. Let's come back to that. I want to look at what else is ahead. Sphere for this point from this. That's pretty legit. I think that one's too easy, though, honestly. And I'm just looking ahead here. Points on the sphere and a plane. Okay. That one's good. I like that kind of stuff. That's good. See how these are all application problems? Every one of them, right? Obviously, what I'm doing is avoiding having to do any more today at this point. um, Yet again, another good one. I'm glad I put so many, and then we're done with it. So, yeah, this will definitely take us a couple days at least, and that's great. That's what it should do. Um, so, I'm done. There's no way we can finish another problem today. 2 problems a day, max. Thank you, guys.